Good morning to my dear students. This lecture L09, it will give you a generalized kinetics of this rate equation, or you can say nth order reactions. So before doing that, I like to formulate the third order reaction, formulate the rate equations of this nth order reactions, third order reactions. Third order reaction may be of three types, a third order reaction may be of three types, say 3A and give you the product, or 2A plus B give you the product, or A plus B plus C and also give you the product. But to make this formulation simple, let us take the concentration, initial concentration of all the substances, especially 2 and 3, taking equal initial concentrations so that the formulation becomes more easy. So we can write the 3A and add. So rate equation in terms of this reactant, we can write minus dA concentration divided by dt equal to K3 into concentration of A. It is the rate of this reaction. Left hand side, negative sign means with the flow of time, with the advancement of this reaction, concentration of this reactant is decreasing, and K3, the rate constant of this third order reaction. 3 implies it is the third order reaction rate constant. So a third bracket means it is the molar concentration, moles per liter, which is the common mode of concentration of this reactant. And it will be 3 as it is the third order reaction. So as before, I have done the separating the variables and integrating within limits. We have minus integration d concentration of A divided by concentration of A to the power Q equal to integration K3 dt. It is the separation of variables. Left hand side concentration of A variable, and it is right hand side T variables. This is the rate at this time T where the concentration of this reactant is this one. So if we do this definite integral within proper limits, then T equal to 0.0, so it will be concentration of A0. This is the initial concentration. Not indicates when the time equal to 0 means initial, just at the start of this reaction. And here when T equal to T, after the lapse of this time T, it is the concentration of A. So integrating this one and doing this and inserting this proper limit, we have actually 1 by concentration of A square equal to twice K3 and T plus 1 by concentration of A square. And this is the integrated rate equation for this third order reactions. You can do it integration by yourself and find out this final result. So far Then we have for zero order reaction, it is concentration of A equal to minus A naught concentration of A plus concentration of A naught. So this is the integrated rate equation for this zero order reaction. So if we write this first order reaction, then it will be the ln concentration of A naught divided by concentration of A equal to K1 and T. If we, for second order reaction, it is 1 by concentration of A equal to K2, second order reaction, K2 T plus 1 by concentration of A square. And for third order, which I have done recently, it is 1 by concentration of A square, equal to twice K3 and T plus 1 by concentration of A2. So these are the all integrated rate equations for zero order, first order, second order and third order. But it is sometimes becomes difficult to keep in memory all the rate constants of this individual order of these reactions. So we like to find out one generalized integrated rate equation, so that from which we can find easily the zero order, second order, third order. First order will be a little bit, first order will create for the first order n equal to 1, here n equal to 0, here n equal to 1, here n equal to 2, here n equal to 3. For first order, it will create some problem, but we overcome that problem by doing some mathematical tricks. Now, better we can find out the integrated rate equation for this nth order reaction, for nth order reactions. So in this case, taking all the concentration of the reactants equal, initial concentration, taking all the initial concentrations of all the reactants are taken equal, we have the NA and give you the product. So this differential form rate equation minus the concentration of A divided by dt equal to Kn and concentration of A to the power n, as it is the nth order of this reaction. N may be 0, 2, 3, but not equal to 1. For this one, it will not be valid. So Kn is the rate constant for this nth order reaction. So separating the variables and integrating within limits, we have minus integration dA divided by concentration of A to the power n equal to Kn, which is constant, and here dt. T equal to 0 when it is concentration of A naught, initial concentration. T when after the time t, it is the concentration of this reactant A. So this integration we can do it very easily. Say minus integration and concentration of A to the power minus n into D concentration of A equal to Kn and integration 0 to T and dt. Here concentration of A0 and here concentration of A. So it is similar to integration x to the power n, x to the minus n and dx integration. It will be x to the power minus n plus 1 divided by minus n plus 1. So instead of x, we can write a concentration of A and put this limit. So this will be minus concentration of A to the power minus n plus 1 divided by minus n plus 1, and the limit is A0 and A. A0 A, and this one equal to Kn, and here integration T and 0 to T. Or we can write minus. If we remove this minus, then it will be n minus 1. So 1 by n minus 1, and putting this upper limit first, concentration of A to the power minus n plus 1 minus concentration of A0 n minus 1 equal to Kn, here T minus 0. So if we bring it downside or the denominator, then it becomes 1 by n minus 1, and it is 1 by concentration of A to the power 1 to the power n minus 1 minus 1 by concentration of A0, means initial concentration, and to the power n minus 1, bracket close, equal to Kn T. If we this n minus 1 transfer here and this term to the right hand side, then nth order reaction then integrated form integrated rate equation becomes 1 by concentration of A to the power n minus 1 equal to Kn n minus 1 T n minus K1, this one will go there, K1 n minus 1 T plus 1 by concentration of A0 n minus 1. This is the integrated form of this nth order reaction kinetics, and from more generalized equation where you can find out all the zero order rate equation, second order rate equation, third order reaction, third order rate equation, but not this n equal to 1. This is valid. N not equal to 1. When n equal to 1, this becomes 0. is 1 and this one also 1. So if you like to put n equal to 0 for first order, then it becomes 1 by concentration of A to the power 0 minus 1 equal to K0, and here 0 minus 1 T plus 1 by concentration of A naught 0 minus 1. Or if we go in numerical, then it is the concentration of A equal to minus K0T. Here K0T, and plus concentration of A naught. So this is the first order kinetics. So from this generalized equation, we can easily get this zero order reactions by putting n equal to 1. So if we put n equal to 2, then n equal to 2, then this one here 1 by concentration of A 2 minus 1 equal to K2 into 2 minus 1 T plus 1 by concentration of A naught 2 minus 1. So it will be 1 by concentration of A equal to K2T plus 1 by concentration 1 by concentration of A naught. So this one, this set for the second order, this is the rate equation. Similarly for n equal to 3, you can also find out this one, n equal to 3. But this, whenever you like to put n equal to 1, it will create some problem. And the problem you can solve by using some sort of mathematical tricks. Say for n equal to 1 means the first order reaction kinetics. So in this case, this term is to be multiplied from left hand side and to right hand side. Then it will be concentration of A naught to the power n minus 1 divided by concentration of A to the power n minus 1 and equal to K n minus 1 and concentration of A naught to the power n minus 1 and T plus 1. You are multiplying constant A naught n minus 1 left hand side, and here also this one, and here only remains 1. Now if you take this log, then ln concentration of A naught by concentration of A to the power n minus 1 equal to ln 1 plus Kn n minus 1 concentration of A naught n minus 1 into T. Taking the log of both sides. But when n tends to 1, it n minus 1 N minus 1 tends to 0. So this term totally tends to 0. When this term tends to 0, so it will be say L1 plus x, where x tends to 0. And this could be modified as, by expanding, it will be simply the x, when x tends to 0. Logarithmic rule. So you can write n minus 1 keeping left hand side n minus 1 into ln concentration of A naught divided by concentration of A equal to Kn n minus 1 and concentration of A naught n minus 1 into T only. Now you can cancel n minus 1 and n minus 1. So this is the problem which is coming up by putting n equal to 1. This has been worked. And now again, as the n minus 1 tends to 0, so concentration of A naught n minus 1 equal to concentration of A naught equal to 0, tending to 0, n minus 1 tending to 0. So it is equal to 1. Something to the power 0 equal to 1. So this one also equal to 1. So finally, first order reaction. For first order reaction, we got the ln concentration of A naught divided by concentration of A equal to K1. Here it will be 1, K1 and K1. This cancels. This one equal to 1. So T. You see, this is the integrated form of the rate equation for first order kinetics. So we can solve for the first order kinetics, for the first order reactions from the generalized one by some sort of mathematical tricks. If you consider unit of nth order reaction, we have minus the concentration of A differential form divided by dt equal to Kn into concentration of A to the power n, or Kn equal to minus d concentration of A divided by concentration of A to the power n or divided by d. This one comes here. So the unit of Kn will be equal to concentration 1 minus n and time inverse 1. If you take this concentration moles per liter, concentration equal to mole liter inverse, then the unit will be mole 1 minus n liter n minus 1 and times second, then second inverse. So utility of this unit of Ka, rate constant for the second order reaction, is very popular. From this unit you can find out the value order of this reaction. You can find out this order of this reaction, which order the reaction is having. Say one example I can give you, the decomposition of decomposition of hydrogen iodide in gaseous state at 556 Kelvin is 3.5 into 10 to the power minus 7 into mole inverse liter and second inverse. So if you find out what is the order of this reaction or this decomposition of this HI, you can equate this power. Say 1 minus A equal to here minus 1 or 1 here coming in there, A equal to 2. So this is the second order reactions. So the unit of this rate constant will give you the order of this reaction. If the order of this reaction is not mentioned in any problem, from this unit of the rate constant you can find out what is the order of this reaction. Next one, another important parameter is the half-life period. Say half-life period or say expression of a T half or T 0.5, 50% decomposition or half of this decomposition. What is the time required for the second order reactions? So in this case, concentration when T equal to T half, concentration of A equal to concentration of A0 by 2. Initial concentration becomes a half, cut in half. Whenever this time is equal to the half decomposition period. So putting here 2 to the power N minus 1 and concentration of A0 N minus 1, and if you bring this one here minus 1 by concentration of A0 N minus 1 equal to Kn and N minus 1 into T half. You can write T half or T 0.50 or 50% decomposition. So it will be equal to this concentration of A0 N minus 1, here 2 to the power N minus 1 minus 1 equal to Kn N minus 1 and T half. So T half equal to T half, you can summarize here 1 by N minus 1 into Kn N minus 1 Kn and 2 to the power N minus 1 divided by A0 to the power N minus 1 and third bracket close. So from this it is also generalized expression for the half-life period. So from which you can find out the half-life period of 0 order, second order, third order, but not this first order. Not valid for n equal to 1. Not valid for n equal to 1. N equal to 1, this one equal to 1, so this 1, it will 1 by n equal to 1 means it is infinity, 1 by 0 infinity. So it is not valid for the first order reaction. From the first order reaction we have to go here. So other reactions, 0 order, second order, third order, you can get half-life period. Another thing is that which is a very important parameter for our find out the order of this reaction. Say T3/4 expression of T3/4, or you can say T 0.5. decomposed, then it is in that case when T equal to T3 by 4, A equal to 3 by 4 already decomposed. So 1 by 4 still remaining. So it is the initial concentration of A0 by 4. This one quarter of this initial concentration still remains to decomposed. And this is, and after this time, this one. So putting here also, we can get the 1/4 into A minus 1 divided by concentration of A0 to the power A minus 1, and this one brings here minus 1 by concentration of A0 to the power N minus 1 equal to Kn N minus 1 into T to the power 3 by 4. So T by T3 by 4 equal to 1 by N minus 1 into Kn, and here 2 to the power N minus 1 square you can write, and here minus 1 you can write also 1 square, and concentration of A0 to the power N minus 1 third bracket close. So it is A square minus B square. This one you can write square terms. So A square minus B square equal to A plus B into A minus B. So this one equal to 1 by N minus 1 into Kn, and here 2 to the power N minus 1 minus 1 and 2 to the power N minus 1 plus 1 and divided by concentration of A0 N minus 1 third bracket close. So one beautiful thing is coming up. Whenever here also it is valid, not equal to 1, N not equal to 1, or 0 order, second order, third order, it is equal valid. So if we find out this T half divided by T 3 by 4 equal to, if we make this one by this one, then this term cancels, this term also cancels, and here this term here equal to minus 1 minus 1, this term will remain. So this term and this one totally will vanish, and it will give this 1 minus 1 by 2 to the power N minus 1 plus 1. You can check it by yourself. If there is mistakes coming in writing these forms, I hope this is quite okay. 2 to the power N minus 1 cancels. This one also cancels. This one. So 1 by 2 to the power N minus 1 plus 1. One beauty of this equation is that ratio you can find out. One beauty of this relation is that you can find out the order of this reaction if you can determine T half and T3 by 4 experimentally. Say, and and this total is a function of n only. So for 0 order, first order, second order, third order, in every case it is equally possible. So if you then next question is that how could you find out this half-life period and 3/4 period? For say for n equal to 0, say 0 order reaction, 0 order reaction. If you plot, I have shown you the experimental data, kinetic data. Here T, here concentration of A. Here T1, concentration of A1, and T2, concentration of A2, and T3, and concentration of A3, and so on. These are experimentally measurable kinetic data. After mixing some at different intervals, different time intervals, you will have to find out the concentration of this remaining reactant, either physical method or chemical method, as we have discussed in my last lectures. So these are the kinetic data, and from this kinetic data you can put here T equal to T along this x-axis, concentration of A along this y-axis, and here it is 0. So for first order reaction it comes like that. Here it is Ta0 when time equal to 0. So for the first order it is a linear form with a negative slope, and this one is the intercept. So this is the A0 by 2, and this one is the T0, and this one is 1/4 and A0. So this will give you the T 3/4. So from this graph, in this T axis, you can find out T half and T 3/4. You put here, then you can find out this end. For the accept this 0 order, for first order reactions, second order reactions, third order reactions, this N2 first order, all these order reactions, whenever A versus plotted A is plotted against T, here the concentration of A0, concentration of A. So this plot will be exponential in nature. So it is the A0. This one A0 by 2. And corresponding time is the T half. And it was A0 by 4. 1/4 of this initial concentration is still not decomposed, remaining undecomposed. So this one corresponding, it will be T 3/4. So by drawing this experimental measurement and plotting in a graph, you can find out this value, these two values. If you take this ratio, then you can find out this value of N. Here also, putting n equal to 0, you will get this ratio, n equal to 1, it will also give you this ratio 2, 3, whatever the value of N, this ratio is still valid. One problem I can give you, this problem, and we are limited to this third order. Third order reactions, whenever I shall study the collision theory, third order reactions requires three body collisions. Three body collisions is rare. So beyond third order means fourth order. Say in that case, so four body collisions required for the chemical reactions, but the four body collisions is impossible. So we are limited with this third order reactions only. The third order reaction only, but very common first order and second order. So now one problem I can give you to solve. Say the decomposition of a gas in a closed vessel, in a gas at an initial pressure, 900 millimeter of mercury in a closed vessel. In a closed vessel at a given temperature. At a given temperature T. The gas is found. The gas is found to be 50% decomposed in 30 minutes. In 30 minutes. And 75% decomposed in 90 minutes. In 90 minutes. This one, initial concentration, initial pressure is 600. So the reaction show that the reaction is second order and calculate the rate constant of the reaction. Clearly stating the units. This has been said in Calcutta University (1985). Now the first question is that what is the order of this reaction? Order of this reaction, so here this T half is equal to, T half means 50%, 50% decomposed in 30 minutes. So it is 30 minutes and it is the 90 minutes. And this one equal to 1 by to the power n minus 2 to the power. So 2 to the power n minus 1 plus 1. This is not n, this is 2. 2 to the power. So if you solve, so this is equal to 1/3. So n equal to so n equal to means it is second order reaction. So it is second order reaction. The half-life period then again T half for this second order reaction, putting n equal to 2, n equal to 2, 2 minus 1, 1, 1, 2 minus 1, 1, 2 to the power 1 minus 1, so 1 by n equal to 2, so it is Kn and concentration of A naught, concentration of A naught. Half-life period is inversely proportional to the initial concentration of this reactant for this second order reactions. Putting here n equal to 2, Kn, so it is K2. You can write K2, second order reactions. 2 to the power n means 2 minus 1 means 2 to the power 2, 1, 2, 2 minus 1, 1, 1 is 1 divided by K2 and A to the power n minus 1 simply n1. Now putting this value, now putting this value K2 equal to 1 by T half into concentration of A naught equal to 1 by A naught is the 30 minute, A naught equal to 30 minute and this one 1 by concentration of 600 millimeter mercury. So this will give you 5.5 into 10 to the power into 10 to the power minus 5. 5.5 10 to the power minus 5 into, the unit will be millimeter mercury to the power minus 1 and minute. So this is the proof. This is the value of this K2 with proper units. So this is all about today's lecture. Next, in my next class, I try to discuss the RNA equations, how the rate constant is dependent on this temperature. In most of these cases, with the rise in temperature, rate constant is decreased. So this RNA equation is very popular for the examination purposes. And I have told several times that the rate constant is constant for this reaction at a given temperature. But if you change this temperature, then rate constant, value of this rate constant will also change. So thank you all for watching my video, and this is the 9th lecture for this kinetics of this kinetic reaction, kinetics of these reactions. So okay, today I complete